Aha! Thanks for joining us today. Not really sure what we're going to talk about, but I need to do some CAD work. So I figured this might be a good time to do a Q&A on CAD, how I use it for designing motors, ESCs, and maybe any questions that you have about why it would be useful. So to start out, I would like to say that I prefer SolidWorks for my CAD suite. And if we go to the overhead cam, maybe we can just get around this in a slightly easier way. But I'm in the middle of designing a new housing. Why? Just why not is really the answer to that. Of course, it's always nice to have some fresh designs, but yeah, just kind of testing it out, so to speak. I have a couple of ideas for some new designs I'd like to implement, and usually the easiest way to do that is to put them into CAD first. So let's see. First, does anybody have any questions about CAD, maybe the usefulness of it, or questions about certain software suites? Let's see here. I have a pop-out chat on my phone, which may make it easier to read the comments. There we go. So far, nobody cares about the CAD, which is fine. So what I'm going to do is continue working on this. We'll actually roll back. I just want to show you. Let's see. I'm going to zoom this in. No, it's not the best looking at a screen. However, it'll be better than nothing. Let's see if we can get a little bit. In the future, we'll have a port from my laptop so that you can see. Maybe we can even figure that out. I don't know if we got enough. Do we have enough inputs on the board? We might have enough inputs to be able to show you what I'm doing on screen. I'll just zoom this in so you can kind of see. All right, so when I'm making motor housings, there's really no one good way to do it. But what I prefer to do is to do a revolve style of extrusion. So we're going to look at the sketch here. Maybe you can see. Let me know in the comments if you can tell what's going on or if we need to hook up directly to my computer. Yeah, we'll just go ahead and get it hooked up to the computer. That sounds like a good plan. It won't take a moment. One moment, please. And I would like to preface before any of this that this design that I'm doing today probably won't be used. There we go. Maybe I'll just start a fresh one. How about I just start a completely fresh design for y'all just for today. All right, let's see how this works. Yeah, let's just do that. Nope, you don't need to see that. You don't need to see that. Yeah, I consider CAD to be cardboard-aided design, computer-aided design. I would say even though it's 3D modeling at this point, it's still computer-aided design. Especially with SolidWorks, you can do 2D or 3D design. There's so many different ways to do it, of course. We're not gonna do that. We're gonna make a new. Can I make a design so that when it turns, it comes to life on a can? You mean like a stop animation? That would be interesting. All right. So if you were looking to 3D print objects, it's a completely different workflow as compared to machining a process. What I'm going to show you today is going to be a machined product, in particular on a lathe or on what would be considered a, let's see, what's the machining work center, machining work center lathe. So this is going to be a lathe that not only has turning functions, but it has drilling and tapping functions, has live tooling on there, either, let's see, what would this be? This would be X direction, so if we've got our object being turned, let's see. I'm going to design a motor housing. So if we are designing an object being turned, this is going to be our Y direction. This is going to be our X direction, if I remember correctly. Let's see, let me think. Yeah, Y, X, there we go. Yeah. Y, X, and Z on a lathe. So if I want to make it easy for the guy that's going to be importing it into whatever software that's either working CAM, then I would make it in my software so that it lines up. This is more important with 3D printing. If you're going to 3D print, you always want the Z kind of facing at you as if you're looking down on the print as it's being printed. That way you don't have to flip it whenever it gets into your printing software. But essentially, the way that I'm going to think about this design when I start up is that this is going to be a machined object on one side or another. And so I need to be careful on how it's designed. This is called designed for manufacturing, and it is really one of the first things that I actually learned when I started to learn how to design. Because there can be all sorts of crazy designs out there, of course, but if you can't manufacture them, then what's the purpose of it? So I have a new one opened up here in SolidWorks. And what I'm going to do is start on the front plane. Essentially, we're going to normal to right there. We got that on the feed now. Watching me in the CAD software on the feed. Excellent. Yes, all right, so we're going to start on the front plane. Really is kind of arbitrary when it's going to be sent off to a machinist. But if I was going to put this into my own machine, I'd be a little bit more careful about that. I suppose I would start. Let's see. Let me look here. It would be. Yeah, if I was looking at it as if I was a machinist, it's going to be the right plane. It's going to be the X-axis that is facing towards us. So yeah, let me just start right there. This is going to be a motor housing. So on the right plane, we're going to start with a sketch of a line. And it's going to be for construction in infinite length in SolidWorks. I'm going to go from that origin and just move it out sideways. So this gives us an orientation line to revolve around. There we go. We got the line. The next thing I will need is another line, and the simplest way for me is to deselect and reselect the line. And the motor housing, I guess it really doesn't matter which way it's actually facing, bearing pocket on the left side, bearing pocket on the right side. If this was going to be made in a machine, if it has at least 2 live tools on the back side, then it's going to be able to do it either way. But if it only has live tooling on the front side, not on the subspindle side, then we would have to be careful which way it's orientated. Of course, the CAM software could flip it around, or maybe they're doing conversational, and I'm getting sidetracked now with things that don't really matter. So what I'm going to do is just essentially make ourselves a pretend can to start out with. It's going to go to here. This is going to be a brushless can, so there's got to be a little step for the stator to sit in. Then it's going to go down. Then we need a bearing pocket in it. And there we go. So it needs to be closed structure. Bam. The shaded area tells you that it is closed in structure. All right, so this is SolidWorks. This is 2020 edition. I can use some other ones, but at the same time, this is what I'm good at. So, I've been using this particular software suite since 2007 or so. Wow, the years roll by. All right. So what we need to do, let's see, bearing pocket, I actually need one more step here because I'm going to attempt what is called blind holes in the face. The majority of motors that I design do not have blind holes because I do not want people to have the false sensation of them being completely waterproof. But let's just go through it on this one. All right, so I trimmed off those little entities that just kind of gave me this extra step here. And now what we need to do is essentially start dimensioning everything. And since it's going to be revolved, I'm going to dimension it from the center. Everything is going to be in radius on the X or Y axis. I guess I'm doing it in the Y. It really doesn't matter. Again, it's being kind of nitpicky. I want an 8mm hole in the face for the bearing pocket. So we do 4mm on the radius. And selected the wrong thing there. Go back to Smart Dimension, make sure nothing is selected. We're going to make the face of the motor in front of the bearing be 1mm thickness. We can go ahead and set the can diameter. We know that it's 36 millimeters for a standard 540, so we're going to cut that in half. Easiest way to do that in SolidWorks is 32 divided by 2. Bam, 18 millimeters. There we go. From face to end, nope, I didn't want that. There we go, one more time. From face to end, I'm actually going to let the software do the calculations for me in a sense. So we'll just continue on. We'll do bearing pocket. The bearings are 16 millimeter bearings that I use in mine. So we're going to have an 8 millimeter radius, 16 divided by 2. One thing that I would like to make note of is that so many companies list their ball bearings as being oversized in their motors. And so far, I've not seen a single company that uses 16 millimeter bearings. They all tend to use either 14s or 15s. I'm sure there's got to be somebody out there that does. All right, we're going to turn that smart dimension off. I need to pull this out just a little bit. All right, so we've got a 5 millimeter depth of this bearing pocket. We have a 16 millimeter, 8 millimeter radius from our center line on this pocket. Then what we will need is some steps for the stator and some steps to make sure that we don't have wires from the stator crashing in. So I know how much clearance that I need personally. This is stuff that if you don't have all your bits in front of you to measure, then it's kind of hard to figure out. But let's see. All right, so this guy, one step at a time. I know that my stator needs a 17 millimeter radius, and these are all nominals. Something that I definitely should mention is that when this goes to a machinist, you can send them a drawing and they're going to machine really whatever they feel like machining if you don't have your tolerances on here. So yeah, this will just show you nominals today. All right, and I know that we need roughly 7.85 millimeters for a distributed wind on the stator that we shall be using for this fake motor. If it was a concentrated coil, we're going to have more interns, and so we will need more space on this. But again, what I am going to assume is that it is a 12-slot distributed wind, and that is going to give us, we just need a little bit under 8 millimeters to pass the coils in this little part right here. All right, so what do we have next? This right here. They're going to be blind holes, so I want to be sure we have enough room from the front to the back for the blind holes. The blind holes I want 7 millimeters longer, so we're going to give 8 millimeters so that we have just a little bit extra room on there. And the rest of these really don't matter. Let's see, our stator is going to slip in right here, so I can do my final dimension. And I know that if we have a 15 millimeter stator that I'm going to want to add, let's see, let's give it a little bit of extra room. Let's give it 12 millimeters on the backside, because I know that I need about 8 millimeters room for the interns, and then we will need a little bit more on the backside so that we can actually get the wires out of the can, although that's kind of debatable, but just give me a little bit extra room. So here we go. This is not a parametrically designed motor housing or anything like that, but we've at least got the first portions. We have the bearing pocket located right here. We have our stator pocket located right here, and we have our pocket for our wires on the interns of the stator to go right here. So the next thing, we're going to go up to the feature tab and do a revolved boss slash base. And it automatically knows what I was going for. We can do a little wheel, mouse wheel here, but you can kind of see what's going on. Bearing pocket's going to be in right here. And we'll just hit this. Boom. So there is our basic motor can. Very basic motor can. I don't have anything on the back end to hold our end bell in with yet. We don't have the stator. We don't have anything inside this can yet, but what we do have is at least a start. So to give myself a little bit of looky-loo here, we're going to say normal to the sketch, and then I am going to change to a hidden wireframe there. So you can see the inside. Once again, here is where the shaft is going to poke through on our motor. This is where the bearing is going to sit, and then we need a space for our stator to butt into with room for wires. Now, before I go any further, I reckon may as well put mounting screws into it. So we will normal to this face. I'm going to change back to the regular view so I can kind of see what's going on. We're going to start a new sketch. We're going to select the plane for the sketch, and I do know that we need a 25 millimeter radius for our bolts, 540 standard. So 25 divided by 2, nice and easy. Oh wait, no, that was, yeah, we're in radius. So there we go. This needs to be for construction because I don't want to use this for anything else. And then if I was a machinist, I'm going to say, if we did a roll form thread, let's see, it is 0.25 millimeter depth of thread. So we would do a 2.75, that is, need to be divided by 2, 2.75 millimeters, so 1.375 millimeter if I was going to do a roll form thread. If this was going to be a cut thread, it's going to be a 2.5 millimeter hole. So, 1.25 on there. It really doesn't matter. We can always just do call outs for threaded holes down the road. Back to it though. All right, we got this one hole. We can either do a circular sketch pattern on here, and we would have, let's say, 6 mounting holes on this, and then we would, cut our holes, or we could just cut one and then do a circular pattern on the actual feature of the threaded hole. So I'm just going to do 4 circles in the sketch and then go back to features, and we will do an extruded cut, and it should select all of those for us. Yes, and it automatically selected 10 millimeters because that is our standard. And I know, since I did an 8 millimeter thickness of the faceplate, that I can do a 7 millimeter extrusion. We're going to hit OK, extruded cut, and then go back to our wireframe and make sure. And we'll just do a, here we go. Flip that around once more. And there's our zoom to fit. Hey, F on the hotkey. Hit F for respects. There we go. So as we can see, there's just enough room right here to avoid our threaded holes. I want a little bit more beef on there though, because I spec those at 2.5. And I know as a machinist in my previous life that that's not going to give us enough room. So what I'm going to go do in here, we'll normal to on this sketch. Either way, it doesn't really matter. Then I'm going to edit that can shape. Give ourselves just a little more room. Just a little more room. So what we're really trying to keep on this little cutout area right here is a way for our ball bearings to be recessed, but also have enough room for our washers, essentially, or whatever you want to call them on the shaft. So it can't be smaller than our bearing because you got to get the bearing into the pocket, but it can't be so large that it interferes with our threaded holes. So I'm going to go, yeah, about right there. We'll call it good. Let's see how it lines up. That's a little bit more beef. I could probably even do, let's see if it'll let me. Sometimes you can select, nah, not so easy. Sometimes you can select the edges of the objects. We'll do it this way. Edge of that, edge of that. It won't tell us. Edge of this, edge of this. There we go. Distance 6.6 millimeters from edge to edge. That should be enough for us. All right. So that was a right-click shortcut. You can actually have it go between all the views real quick there. But yeah, that should do. That should do. So now it's pretty plain looking, pretty plain. We'll go back to a regular view. But this would actually work. Once we had a call out on these holes, it would still mount up, but it really needs to look a little nicer. So we're going to normal to on here, and I'm just going to draw essentially where we're going to cut. Let me run through the comments here real quick and see if I have missed anything. Doo, 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 doo. All right. So good question about tolerances. How much will performance improve if you see the tolerances are tighter? Really depends on where the tolerances are. If we're talking about a bearing pocket, we want to have a slight interference fit about 2/10,000ths of an inch so that we can get the bearings out and we can also get them in without it being sloppy in the hole. If it was oversized, let's say 2/1000ths of an inch, there's going to be a lot of radial play. There's going to be, and when I say radial play, I mean like this. So this would be axial in and out. This would be radial on a motor. This is a radial flux motor design. So we would have a rotor on the inside, and then we would have our stator on the outside. Really doesn't matter which direction that is, but the flux goes along the radius of the shape of the motor. So a lot of the tolerances on the motor are needed on essentially the radius. If we have, let's say, too loose of tolerance here where the stator goes in, we want it to be a slip fit, but we don't want it to be too much of a slip fit. If it's, let's say, half of a thou, 5/10,000ths of an inch, that should be fine enough for horseshoes and hand grenades. I would prefer to see more like 2/10,000ths of an inch slip fit. That way we don't have a lot of variation in our stator, but stators a lot of times are going to be undersized and oversized just a little bit in a way to where you can't have it too tight, or else some of them just will not assemble, or you'll end up damaging the stator when you try to press it in, and it's just kind of a big hassle, of course. So what we need to do is, it's a balancing of tolerances on so many levels. If the stator ends up sitting kind of crooked off to one side, like let's say we did just 5/1000ths of an inch tolerance on there, and it's like a hot dog in a hallway, then our stator, when we glue it in, is going to have the ability to kind of slip one way or another. And if there's 5/1000ths of an inch on the radius for tolerance, let's just call that on the circumference, so 2.5 thousandths of an inch, then that means our stator could be slid over that much, and then our rotor would actually be misaligned in the middle of the stator by that much as well. And that's going to give us a really wonky back EMF of the motor, because essentially one half of the motor is going to have a stronger back EMF than the other half of the motor, and it'll just be a mess, just a mess. So in a lot of ways, the ability to assemble our motor is going to determine what sort of tolerances that we need. And then beyond that, just making sure that everything is actually concentric with one another is the more important issue. So the bearing pocket needs to be concentric with the stator pocket, and the stator pocket needs to be concentric with the outside of the can, and the outside of the can needs to have these bolting holes concentric with itself, so that when you mount it up, that it is not off center, because that could really screw with your pinion mesh. Let's say you mount it in a TRX4 where they make a lot of assumptions on the concentricity of your motor. If you mounted it in, let's say, these holes right here, it's going to have a certain mesh. And then if you mounted it in these holes right here and everything wasn't concentric with each other, then it would have a completely different pinion mesh, just depending on how bad our tolerances were. So yeah, I'll just continue on with this, but that's a really good question about tolerances. Typically, yes, better tolerances are going to have a higher quality motor, but they have to be the right tolerances, and they have to be the right tolerances with respect to the rest of the motor too. So evidently, engineering motors isn't easy, I guess, but you do something enough times, then you get used to it. All right, so what I'm going to do is actually make a cutout on the face, because this really plain looking motor bothers me. So we're going to do 3.5 millimeters on that, 3.5 millimeters on this circle, and then I am going to do a 2-point circle between these guys. And then you can see how this circle moves around. Since I have it as essentially, a tangent point or whatever to the edges of these, then I can pull it kind of wherever I need to. And while I'm thinking about it, I want to see the wireframe. Yep, that screwed me up real nice. Whoops. All right, we're just gonna ignore that I did that. We are going to shut that off. Gonna delete that guy and try once more. So 3-point, gonna go back to this, 3-point on the edge of that, 1, 2, and you can see our interior bearing pocket here. If I did a cutout that got into the bearing pocket, then it's gonna show our bearing on the inside of, or I'm sorry, on the outside of the can, which, I mean, maybe that'd look cool. We're gonna go for ultralight on this guy. So this is gonna be a weird looking motor cut out, but that's fine. And I'm kind of thinking about it like a machinist here. We just want some tangents. We just need to cut away some parts. That's all we need to do. But this needs to be an enclosed. Let's see. Oh, shoot, I did that wrong. Let's see. Can I go back? Can I go back? Yes, I can. All right. We're going to trim these entities once more. Boop and boop. And boop, there we go. We have a closed form. All right, so I'm going to say, hey, that's good. We're going to go back to this mode, turn a little sideways, and now what we can use is the extruded, cut. There we go, extruded cut. I know that we only have 7 millimeters to work with. I'm going to say 6 millimeters. So that it doesn't get into any of our good stuff. That should give us just enough room. It won't be too thin. Again, this is where experience kind of comes into play, knowing how thin is too thin on a face. All the years that I machined our puller housings in-house, I really got a feel for what is too thick and what is too thin. And of course, it depends on the materials as well. But there we go. So we have one cut on this guy. We're going to press F for respects. We're going to go back to this view. Oh, look at that big old cut where the bearing is. Maybe I should import a ball bearing as well. See how it looks. Yeah, that'll be interesting. Whatever, this is just for fun. Now what we're going to do is we're going to copy this into a circular pattern around the can. So direction 1, basically any round object. We only want 6 of these guys. There we go. Oh, look how lightweight and fancy that looks. It's like some revolver cylinders. But, that's going to get a whole bunch of crap inside the motor. And I'm actually a little worried about how much interface we have here. Yeah, I can't move the feature. Let's make sure we want to silence our phones, huh? Yeah, whatever. I'm gonna adjust this a little bit. So we go back to our sketch. I'm gonna normal to, and wrong sketch. Whoops. We're gonna go back to our sketch cut. We're gonna normal to. We're gonna edit the sketch, and since I did not put any limiting dimensions, which I should, so that this doesn't do funky stuff. Okay, we're going to put those back at 3.5 radius, and now what I can do is literally just drag this around, and all right, I'm going to drag the center point. That'll help. So as you can see, it's kind of like, I don't know how to describe that. Since I put the points as tangents to each other on these curves, I can just drag this around, and it looks nice. So let's just see how that looks. Boom. That's nice. Still has a little bit of, as you can see, a little bit of hole there. So we're going to go back in. And there's ways to actually make this, self-solve for a lot of these dimensions, but this is close enough for horseshoes and hand grenades. So there, that's a neater looking face, but these corners are all going to be sharp. And if you don't tell a machinist to do something about it, they're not. So what we need to do is either use fillets or chamfers. Let's see. I'm definitely going to want to chamfer. I'll just do this entire face. And what that is going to give us is both chamfers on the holes, which we always need to make sure that it is really easy to start your threads, and also for the threading operation when they're actually making these in the CNC. If you don't have a chamfer on the edge of these holes, it's just, as a machinist, I would hate you as a designer. And I may actually add them myself. Whoops, I selected too many things. It is getting mad. Remove. We'll just clear them all. There we go. All right, that should work. Oh, what? You can't do it? Geometry, 0.5 millimeters. That should work just fine. Why aren't you working just fine? I've done this before. It doesn't like it. Geometry conditions. All right, so we're just going to have to go through, manually select. There we go. We probably want a chamfer on the edge of that. And let's see if it'll let me do this. No, it's not going to let me do that. I'm going to have to come back and do a second chamfering operation. And maybe that's why I didn't like it. The boundary in between these, sometimes it gets fussy. So we're going to do another chamfer. Let's see if it likes it. Yeah, for some reason it's not liking this. I may have to adjust my dimensions a little bit, but we're going to try. You don't know until you try, and sometimes it's difficult to figure out what the software is trying to tell you. Because believe it or not, I'm not a formally trained engineer. Yeah, it doesn't like that either. So I'm going to have to go back once more. We shall look at this. Normal 2. Edit the sketch. And my assumption is that this needs to be a little bigger. And if I was fancy, what I would do is make both of these radiuses be equal. That way when I changed one, it would make a change to the other. There we go. And the sketch is overdefined because I have... There we go. We're going to delete that. And now I can go in and we can make these equal. Equal. Do it. Done. All right. So I can change this to 3. Bam. I can change it back to 4. Bam. All right, so we'll try once more on the chamfer. Will you do it? You're gonna let me? It's not letting me. What if we flip the direction? No. Well, what if we go to 1 millimeter? Nope. Sometimes we can get rid of this. Nope. How about 0.25? Anything? It's given me nothing on this one. So evidently I did something wrong. Again, I'm not a formally trained engineer, so oh well. We'll forget about that for the moment because we need to chamfer this edge. There we go. 0.5 millimeter. That's looking a little better. So my question is still, why won't it let me chamfer that? So, because I am a glutton for punishment, I'm going to see if I can figure it out. All right, 0.5 millimeter, 45-degree angle. Nothing wrong with any of these. Won't do it there. Distance, distance. There we go. Offset face. Face to face. No. Yes. See if it likes this way. It probably won't. Nope. Oh well. Tell you what, we're going to move on that one. But what we do need is a way for a cutter to get in here. Because again, a machinist is going to have to make these. And this hard radius, or this hard edge which has no radius, is an impossibility to machine unless you have a tool that has no radius on the edge, which they're made, but as a machinist, I don't like them. It's really easy to overheat the tips. And besides that, they're still going to have a little bit of radius, whether it be a 5 thousandths of an inch or whatever. But I know that the machinist is probably going to want to use a 3 millimeter ball nose to clear off this face. I mean, that's what I would use if I was a machinist. How about y'all? So what we can do is essentially go through and, yeah, so that's probably why it's not liking it. I see what's going on. Yeah, well, we also have a 1.5 millimeter. Oh, no, no, that's what we'd want if it's a 3 millimeter in mill. There we go. I'll go ahead and add these in, even though they're not doing anything. All right, so that didn't do what I really wanted it to do, which would be to add in the radius all the way around, because otherwise it's going to be really hard to machine this sucker. We want to make sure that this is a manufacturable good. So we'll try one more time. We're going to edit this feature. We're going to remove all of these, clear the selections. Symmetric, we want tangent propagation. There we go. Now, will it continue? It's not continuing on. Let's see though. I bet it has something to do with this. So we're going to normal to, we're going to try once more. Go back to, oh, let's just say 3. Let's see what happens on that. 3, boom. Hey, that was it. I kind of figured. Yeah, sometimes it's just a little too tight for it to do the operations that we're asking for. I would still want to go through. I'm going to see if I can get this entire face. Let's do a full preview. Yes, now it's working. So I just had a little bit too tight, too much tightness in between some of the features. You know, this is going to be threaded out essentially to the fullness of that chamfer. I would think, yeah, wait, not quite, halfway through that chamfer, because we've got a 2.5 millimeter hole and then a 3.5 millimeter chamfer edge, which means a 3 millimeter, 3 by, let's see, what is it, 3 by 0.5. Yeah, that's going to be right in between. All right, all right. So, getting a little nicer looking. What do y'all think? That would actually be able to house some motor parts. And let's look at the selection here. So as you can see, we got the blind holes going in. They won't be able to be threaded all the way down, even with a blind tap. There's still going to be a small section where they can't reach. And, you know, it's a bunch of heaviness that's going to be in here. There's our bearing pocket. Here's our clearance for the bearing pocket. And then our clearance section for our stator wires on a distributed wind, like I said. And then the section that is going to actually have the stator slide in. There we go. We are getting much closer. So the next things that I would need to design on this is going to be the wire exits on the can and a way for the end bell to attach. Of course, we're going to need the end bell. I would need to have the stator and the rotor already designed so that we know exactly where everything needs to place, because without a stator and a rotor, you only have a housing. And what are you going to be housing? Well, that's the stator and the rotor. So kind of, you know, chicken before the egg problem, or egg before the chicken in this particular case. So let's just finish up with a little bit of fanciness. I think that's going to be a good way. And, you know, we can always do a modification to the outside of this motor. Let's see, there we go. So what I want to do is just add some ribs to the outside. There's a lot of different ways that we can do it. My temptation is to always add them into this revolving sketch because it's pretty easy to accomplish. So that's just what I'm going to do. I'm just going to do that. We're already normal toed. Now we're going to edit that sketch. Yes, and I want some ribs. I want some rib meat. Let's see. Oh, I should look back. We have. We're going to discard these changes. About right there. What I want to do is make sure I'm not adding features in sections where they don't need to be added. So we're going to go back. We're going to edit this. So yeah, about right here. As long as I start my ribs in this direction, what I will do is a teeny tiny circle. Oh no, this is going to be a pain in the butt. Nope, nope, nope. I changed my mind. I changed my mind. What I am going to do is just a whole new sketch. Okay, this one? Yeah, there we go. Cool. So we're going to sketch. We are going to sketch on the plane that we are currently looking at, which would be the right plane. And now essentially, let's see, what's going to be my easiest way? I always do this in so many different ways. But I'm going to say, oh, we come off about 1 millimeter. 1 millimeter. This needs to be for construction. And I'm not sure if it grabbed the edge of that can or not. No, it didn't. Let's see if we can. Bullocks. Oh well. We'll freehand this one. Ooh, F for respects. There we go. Yeah, we'll just freehand it. Delete. And we're going to start a circle, yeah, about right out here. So again, this needs to be a machinable item on here. And you can picture the nose radius of the tool having to go in as it's spinning in the lathe, having enough clearance. So what I just said, 1.2 millimeters, that is going to be, our minimum radius of a tool, and a normal tool is going to have a 1 millimeter radius on it if it's like a grooving tool or something like that. So I know just from experience as a machinist that this will work. And what I shall do, just to make this easy, and it doesn't need to be much. This is just for looks, mind you. We're going to do a linear sketch pattern. We're going to reverse our direction, and then we're going to do, let's see, how many millimeters? Let's try 5. Those are close. Those are close. Again, this is just kind of a looks thing, so it's really not critical as long as we're not taking too much material out of the can. 4, 3, yeah, those are nice and close. I like that. How many instances? Enough to go to almost the edge of the can. We're going to have some other machine features that retain the end of our housing, so we can't go too far. We still need a little bit of bolting room, if you will. It could machine through those features, but it's just not a good idea to have features overlapping from a machinist standpoint. As you can tell, there's a lot of things in design, if you're designing something to be manufactured, that you kind of have to know how things get manufactured. Otherwise, you don't know where your problems may be. So now we get to do an extruded cut. We are going to do all of those guys, select the contours. We can just kind of, boom, select those contours. I didn't like that. Oh, well. Direction. Oh, no. Revolve. I need revolve cut. I hit the wrong one. There we go. Axis of revolution. Since that other line that I did is hidden inside of another one, typically what we would do is have a new axis on here. So I will go ahead and put in some reference geometry. Oh, got to get out of that. Haha, neat. We're going to add some reference geometry. We do need an axis. It is going to be the intersection of two planes because of the way that I made this, the top and the right. There we go. There's our axis. Oh, what? There we go. Now, we got it. I'm going to move this underneath the axis. So now we can do a revolved cut. And maybe, is it going to know? Haha, here we are. Maybe not the easiest way to do it. There's certainly not only one way we can do things. And we are going to hide all types. Where is it? This is a slightly newer. This is a slightly newer CAD software for me. I've been using a older version for a little bit. There we go, hide all types. Now then, look at that. What do you think about that? And we can add a lot more features as well. I've got other tricks up my sleeve, but as far as random old brushless motor housing, that's at least a start. Now it is bothering me that we don't have chamfers on that bearing pocket edge. Of course, we can't have a hard edge on here. There's got to be the nose radius of the tool. So I'm going to say, what, half millimeter? Half millimeter should be enough. And we are just going to break all of these edges. Bam, break them. Actually, that one I won't break. That's an outside edge. It doesn't have to be broken. It's also an outside edge that supports our stator. So preference that it is not broken. And I'll need to do a smaller one. This is all half millimeter radius on these. Just the little things that you don't see in design. It has to be done, though. We do have a chamfer on the outside, but yeah, that breaks all of our edges except for that guy right there, and that's pretty good. So let's look at this again. Whoa, new mouse. We're going to go through, we're going to look at the wireframe. Oh yeah, you can tell what's going on there, right? Just as easy as pie to tell. Oh yeah, even better. There we go. There's, kind of a cartoon view. And if you want to be fancy, and I was going to post something up on the old Facebook and YouTubes and all that, then we would do, let's see, we can do different appearances on there. We can do colors. We can do textures. Yeah, whatever. I'm going to go back to this, and let's see, what does real view graphics look like? Oh, look at those fancy shininess. That's weird. Every time I let go of that, it zooms out. Let's do shadows in shaded mode, ambient occlusion. Let's do perspective. Let's do cartoon. Look, everything all at once. It looks fantastic, doesn't it, guys? Maybe no ambient occlusion. We don't need perspective. We don't need shadows in shaded mode. And cartoon is rather weird. Let's see. Any difference? Okay, so we can see a little bit better contrast with cartoon at least. And I guess wherever the sun is in here, which you can change. All right, I think that's good as far as the design. To get into the rest of the nitty-gritty, I'm going to have to do an actual assembly, which maybe we can do a fake motor assembly in the future. Or maybe a 3D printed item in the future as well. I know that most of y'all are going to have 3D printers. That's, more of what you're into. But this was a revolved object. This was, something that's going to be CNC machined on a turning center, so it's going to have a lathe that gets in for all these operations, and then we would have to have the milling operations on the side that get in there. So, yeah, like I was saying during the design, there's got to be a lot of design for manufacture that is a little bit more difficult until you actually send things off or make things yourself. And then you get samples back and you're like, no, this won't work, because a lot of times a machinist will make it as best as they can. And if there's not a lot of communication back and forth, because that just increases the price, that they'll just say, hey, these features must evidently not matter because I can't make them. So here you go, to the best of my abilities. This is what you asked us to make. So I'm going to roll through the comments a little bit, see if we got anything else that jumps out at me. A lot of comments here, a whole bunch of comments. I need to reload our comments. There we go. Question about the Copperhead 10. When is my version of the Copperhead 10 coming out? I do not know. I do not have control of that engineering process. I am merely giving them all of my wants and needs, and Castle is working at their own pace. So if it gives you any idea, my first sample was supposed to be delivered in last year, Thanksgiving time. I don't have my sample yet, but I'm not the one doing the hard work, so they'll get to it when they can get to it. I am excited for it, though. We've got a lot of cool features. All right. What else we got? CAD meaning cool ass drawing. I like that. Trying to install V2 revolver in the CR12 and the stock pinion doesn't fit. You need to get a 1/8" pinion, and I'm pretty sure they use 48 pitch on there. So an 1/8 bore is just a standard pinion that you would find on pretty much any 10th scale vehicle. That is something that is different for the CR12. Just the pinion bore. Guy on a Moose's RC Adventures. The machinist's worst enemy, the engineer. I've heard that a lot of times. I got some engineer friends, I got some machinist friends, and there's always kind of that, like, head button between the two facilities. The best machinists are the ones that know how to engineer, and the best engineers are the ones that are machinists. But in this day and age, usually people can't do both, because you spend all your life, learning to be an engineer, and then you get in that position where you're an engineer, then a lot of times you just don't get the ability to go into the machinist's room and work the machine. The machinists don't want you touching their machine. You're a freaking engineer. What are you going to do? You're going to crash that thing the first time. You're going to be entering in, oh, I need to put this end mill in. Let me bump it against the tool. Oh, whoops, I put it in the rear tool holding spot instead of the front tool holding spot, and now we just crashed the machine into itself. It's happened before. So yeah, that is one of the upsides of being self-employed and owning lathes and mills and machining a lot of my own parts, machining the puller housings for many years. The big advantage that I have on design work is that I understand, hey, how are they going to make this thing? I know how they're going to make it. I know what kind of machines they likely have. So that's yeah. Hey, new Sherpa build vid dropped today to the HH channel. Yes, thank you for letting me know. I didn't see that yet. Of course, I recorded it. I was here when it happened. All right. Let's see. Question about the 1415 2400 kV from Castle and Axial Rift. Would the 540 XL 2100 kV offer more torque? Technically, yes, it has a longer stator on there. However, at that link of the XL motor, there is less wire fill. We just can't fill it up with copper because the stator is so long. We can't pull a full bundle of copper through. So the L series motor is actually better on torque density, even though it's a shorter motor. Now they do run warmer because it's a smaller motor. There's less ability to dissipate heat. However, the torque production and the resistance, if we're comparing kV to kV, is going to be better on the L version. Now, is that going to be plenty in Rift? Yeah. Honestly, 2100 kV either way. So if you want to get that XL version, then get the XL version, because I know we do have them, and it will work just fine, and it will run cooler than your 1415 from Castle. As far as the idealized torque output, I wouldn't say it's optimized. However, like I said, you could choose the L or the XL version. They would both work just fine. All right, anything else we got here? Hey, guy on a Moose's RC Adventures must be a machinist, because he would use a solid carbide 2 flute with a 15 10,000ths radius or 1.5 thousandths radius on the cutter tip. Yes, that would certainly work on there. However, I know my machinists, they're going to want to use a ball end. That's it's going to leave streaks on there. Maybe they'll just use 2 tools, whatever. That is a good point. Maybe I could just specify something with a little bit less radius on the side. I kind of like the way this looks, though. They could use a 0.5 millimeter radius, 10 millimeter for all that mattered, I guess, for this, as long as that radius fits in, and the radius fits in there. We got 4.72 radius on there, so it's going to have to be less than a 9 millimeter cutter to fit. 8 millimeter with a 0.5 mil radius on the nose, or a 0.5 mil radius on the cutting edge would work. Yeah, machinist talk. I love it. All right. Let's see. That's about all for the comments right now. And yeah, I see a lot of CAD designers in here. Tooling designers. I like to see it. Probably my favorite thing is designing things. Just it's such a satisfying process to be able to make something in CAD, even if it's just 3D printed. It is such a satisfying process. Or in this particular software, I would use the CAM plugin for my simple machines, because it does 2.5D machining. It's not Mastercam. It is HSM Expressworks, I want to say, which got bought out by whoever owns Fusion AutoCAD, or not AutoCAD. Y'all know who I'm talking about. And now they're trying to force me to buy it, of course, every time. Oh, you need the extended package. Oh, you need to pay us $8,000 a year so that you can machine. That's, yeah, a little much for me for prototyping because my other computer, which has been running for over a decade with SolidWorks and my CAM software, still works because I don't plug it into the internet. And it'll output for any 2.5 axis machine or 3-axis little CNC mills. So that's what I use. Works just fine. All right, I do thank y'all for tuning in. I hope this shed a little bit of light on some of the design processes for making motor housings. One of my favorite things to do. And maybe I will work on something a little special for y'all after this because we should probably work on a new motor line. What do you think? Let me know in the comments. As always, do thank you for tuning in. Have a good day.